Welcome to our Conservation of Energy Lab. What we're going to be doing is we're going to be raising a ball and dropping a ball. And what we're doing is we're raising the ball, giving it this initial potential energy. So we're giving it this gravitational potential energy, this MGH. As the ball falls, the ball should give all of its energy into its motion, its kinetic energy. So what we're asking here in your prediction, before you do this experiment, is I want you to ask yourself, is energy conserved? If it's conserved, then you're saying that all the energy before goes into the energy that's after. That energy is not created nor destroyed. And if so, if energy is conserved, does this equation up above, does this hold true? If not, what equation do you need? So pause this video now so that way you can write in your prediction, write in your answer to this guiding question before you do this experiment. So now that you've written in your guiding question, I have here our list of materials and our procedure for following this experiment. We're going to use this ball, a motion sensor, a program called SparkView, and a metal grate. The metal grate is going to protect the motion sensor as the ball falls. We connect the motion sensor to SparkView. That is the program we're using. We set up a velocity versus time graph. We raise the ball 1.5 meters, drop the ball, and we're going to collect the best velocity data. We're going to repeat this 3 times. So we're going to get our velocity and then get the average of those. So the ball is about 500 grams and we're dropping it from a height of 1.5 meters. So I'm going to use this program SparkView to collect this data. So that was run number 1. So you can see in this region right in here, this is right where the ball is falling. And that is the point in time where we're going to analyze that data. But let's get the other data points here. Once again, we're going to be looking at this region where the ball is falling, and that's going to be the points we're going to be interested in. Let's get another data point. And let's get a 4th one just because. That 4th one doesn't look that good. We're going to get a 5th one. That looks much better. So now we have access to this data. And what I'm going to do is I'm going to look at this data and we're going to analyze it. So I'm going to select the tool to highlight this data. As I highlight it, I want the region where the ball was falling. This is the point in time where the ball was falling. And in this point in time, I want the lowest velocity, so I'm going to get the minimum value here. This minimum value, this 4.33, that's going to be the velocity that I'm going to have as one of these final velocities, so a negative 4.33. I'm going to look to now another data run. Going to run number 2. Once again, we want this point in time where the ball was falling. So while the program now has ceased to work, I still have it on a separate device, so I'm going to do the same process and pulling out those velocities. So I have this negative 4.33, I had a negative 4.12, then I'm looking now in my run number 3, and this gave me a negative 4.23, and I have a 4th data point of a 3.89. So all these were negative because the ball was falling down during all these times. And I want to choose the final velocities that kind of are close to one another. So I'm going to get rid of this 3.89, and instead I'm going to count the other 3 as my velocity that I'm going to use. So I'm now going to take the average giving me an average of a 4.22 or 23. So I have now the average velocity of a negative 4.22667, so it's about a negative 4.23. So that's that velocity that we're getting. The potential energy is this 7.36. So initially we have all the energy in this gravitational potential energy. So there's 7.36 joules of potential energy. What I'm going to do here for this kinetic energy, this is where I'm just going to calculate the 1/2 mv squared. So the 1/2 is 0.5 times the mass, which is 0.5, times the velocity squared. So that's going to be that 4.23 squared, giving me a 4.47 joules of energy in the kinetic. So we were asked this guiding question: is energy conserved? And then, if so, does this equation hold true? So we've already calculated the potential energy and this kinetic energy, and we're seeing that they are definitely different. So the kinetic energy is different than this potential, where the potential has 7 and the kinetic has 4. So if I was to come up to you and ask you to make a trade, I give you $4, you give me $7, hopefully you won't make that trade. Hopefully for you. Hopefully for me, you would make that trade. But we see that they're not equal. But we do know something about energy in the system. We do know that the total energy of the system has to be constant, where some energy is going to get lost to the surrounding parts of the system in the form of air resistance, that air friction. And some of the heat will get transferred into the particle motion. We may have been able to see it on our graph. If you see the graph here, the motion sensor even picked up some of the motion in the metal grate. So that metal grate was vibrating. And that vibration is then some of that energy that's transferred. So this energy went into the external parts of the system, this particle motion. So while the particle motion can be called heat, it's also going to be called this EINT, that internal energy of the system. So then we're being asked our guiding question once again, where we're asked, is energy conserved? And what equation do we need to describe the scenario? So we have these sources other than our lab. So this is essential in getting to this CER, because all we found was that 7 doesn't equal 4. But we do see that this article has some good stuff about this conservation of energy, and there's a whole lot of reading that's going on, and I would like it if we read a lot. But if we only read these 6 words, the total amount of energy is constant, then that right there would be fantastic. Total amount of energy is constant. So when you talk about a system, the total amount of energy in that system is constant. So when we're going to write up this CER, we need to write up something answering this guiding question. So the question is asking 2 things. Is energy conserved? So we need to answer that. And energy is conserved. What that means to be conserved is the total amount of the energy of the system remains constant. So the energy of that system is constant. It's one of these laws of physics, laws of science. So then what we have to say then to answer the second part is the equation will need to have something added to it. So we're going to need to add another term in the form of heat. And then we need to say, well, what the equation was before. I just copy and pasted from above, that this mgh equals 1/2 mv squared. We just need to add in an additional term, heat. So the energy before was that 7.36, and the energy after is now this 4.47 joules. If we were to say that, then that's not true, but it's this 4.47 plus something. That something is the difference between that 4.47 and the 7.36 that you had initially. These values must equal one another. The initial has to equal the final. So you have to add an extra term here of heat in order to make these be equal. Getting to this important term here that we need to state in order for this to be true. The energy of the system must remain constant. This we got from that article. We need to say that because otherwise this whole laboratory experiment doesn't mean anything. The laboratory experiment only shows that energy would not be conserved unless we had some outside knowledge. So in these CERs, you can get some information from outside sources to help answer that guiding question. But you also need to tie in the laboratory data. Otherwise, once again, the lab itself is not called for. So once you have this CER, you are done with this laboratory experiment.